Hey students, in this video I want to explain how we decide when a linear map is surjective and or injective. So a linear map in this case here is a function from Rn to Rm which sends a vector x1 up to xn to multiplying with the matrix A. So in this case A is an m by n matrix, and I will assume that we already know what the matrix A is. So in other notation we say that A is a matrix of F, but in the following I will always just use A for the name of the matrix. So let's recall first what surjective and injective means. So a function in general from one set x to another set y is surjective if for all elements in y there exists one element here in x such that f of x equals y. And this can also be described by using the so-called image of this function. So the image of this function is precisely those elements here in y, such that they exist in x with f of x equals y. And then this definition of surjective just translates to saying that the image of f is exactly y. So everything here is in the image. So for example, if we have these two sets, so let x be the set of the elements a, b, c, and y is the set of the elements 1, 2, 3, then I can consider a function from this set to this set by, for example, sending a to 1, c to 2, and b to 3. So this means that f of a equals 1, and so on. And in this case, what is the image? Well, the image are all these 3 points. So in this case, the function is surjective. But if, for example, b also gets sent to 2, so this map here now satisfies f of a equals 1, f of b equals 2, and f of c equals 2, and therefore this is not surjective because in this case 3 is not in the image of f. So in this case the image of f is exactly these two. So this here is the image of f, which is just the set 1, 2. Okay, so this is surjective, and now injective. So a function is called injective. So if again I have a function from an arbitrary set x to an arbitrary set y, we say this is injective if if two values here in x are different, so x and x tilde, then also f applied to them are different. So the meaning f of x is not the same as f of x tilde whenever these two x are different. And this just means, so in other words, that this f doesn't send two different elements to the same element in y. So in this case, this here, of course, is not injective because we see here, so in this case, f is not injective. Not injective because f of b equals f of c, where in this case we can say it's 2, but b is not c. And also this example here is not surjective. Okay, but now if we have a linear map, so if we have something like this, then now the question is, how can we actually decide if this linear map is injective or surjective? And this will depend, of course, on the matrix A, but it will also depend on these numbers n and m. And we will do 4 examples for this. But in general, so there's a recipe you can use. So there's a general strategy to decide if this linear map F is surjective or injective. So to check if the map is surjective, we want to calculate the image. So we want to see what is inside the image, meaning for which elements y, so which are in Rm, can we solve this equation here, ax equals y. Because ax is exactly f of x. And then the image are exactly those vectors in Rm, such that we can solve this linear system here. So what we are trying to do is we try to solve this linear system for an arbitrary vector y. And for this, we consider the row-reduced echelon form of the augmented matrix. So what we do is we always just write arbitrary y1 up to ym here on the right side, And on the left side, we just write the matrix of the linear map F. And then we will do some row operations to bring it onto row-reduced echelon form. So the left side will look something like this. So I will have some pivot elements here. And here on the right side, I will have some stuff. And this stuff here will depend on the y's. Yeah, because in this row operations, I subtract rows from each other, multiply rows with some numbers. So this stuff here are just some combinations of these y's. And now, having this row-reduced echelon form, we can then decide if we have a solution. So one case is that here in the row-reduced echelon form, we don't have any 0 rows. So if there's no row on the left side which is completely 0, then this means that each row here contains one pivot element. And this means that the corresponding linear system always has a solution. And therefore, for any y, this linear system has a solution, and therefore every y in Rm is in the image. So this means the image is Rm, which means that F is surjective. So if there are no 0 rows here, well, in this picture here there is a 0 row, but if there are no 0 rows, then it's always surjective. But in the second case, if there's a 0 row, so if, for example, here the last row is completely 0, then in the same row there will be some expression here which depends on the y's. And then this corresponding linear system just has a solution if this stuff here is 0. So then the image of F will be given by all vectors in Rm, which satisfies that this thing here is 0. And this thing will be some, for example, 2 times y1 minus 3 times y2 needs to be 0. But it could also be that there are several rows here. Maybe the last 3 rows are completely 0, and then there are 3 entries here, and all of these 3 entries need to be 0. So I get 3 conditions on the y's, which I will all need to write down here in the image. And therefore, in this case, the image will not be everything. So if this is not already completely 0, so if it depends on y, then the image is not everything, and therefore F in this case is always not surjective. And now, how about injectivity? So if we did this here, so we already have this situation that we know how the row-reduced echelon form looks like, and we decided if the linear map is surjective. At this point, we can also already decide directly if it's injective or not. Yeah. So if we take something in the image, this means this here has a solution. Then there are 2 cases. Either this solution for a given y is unique, and if this is unique for all y's, then this means F is injective, because then for a given element y, we can just find one x. But if there are infinitely many solutions, then this means F is not injective. And this we can also see in the row-reduced echelon form here. So assuming we have some element in the image, so we don't need to worry about these 0 rows, then we just need to look if we have some free variables, meaning there are some columns here which do not contain a pivot element. And if this is the case, then we will always have infinitely many solutions, because we can choose the free variables freely. So we always at least have one solution, infinitely many solutions. Okay, but now let's do some examples to make this clear. So we start with this simple example here, which is a linear map from R2 to R2, which sends this vector x1, x2 to multiplying with this matrix here. And now we want to calculate the image. Yeah, so the image. So we try to solve. So maybe first let's give this a name, A. And we want to solve ax equals y for some given y, which is y1, y2. Yeah, so we want to consider this augmented matrix here, which in this case is 1, 2, 3, 4, y1, y2. And then I want to bring it on row-reduced echelon form by, well, in this case I take 3 times the first row and subtract it from the second. So here I have still the same first row. Here I got 0, and now I take 2 times 3, which is 6, and subtract it from 4. So I get minus 2, and here I get y2 minus 3 times y1. And then what we can do is, for example, we can add this to this. So we can add this row there. And then we see we have 1, 0. And now we are adding this stuff there. So we get minus 2y1 plus y2. And here we still have this. And then we can divide by minus 2 to get this here. So the first row is the same. And the second is minus 3/2 y1 minus 1/2 y2. And what do we see now? Well, we don't have any row here which is completely 0. So this means that we can solve this actually for any y. And we can also see that we have exactly one unique solution, because no matter what y1 and y2 are, I get the solution, and the solution is uniquely determined by x1 equals this and x2 equals this. So in this case, the image of this linear map is everything. So this is R2, so therefore f is surjective. And for each y in R2, there is a unique solution. So there's a unique x1, x2 with f of x equals y. Therefore, f is injective. Yeah, and we could even say what this here is, because we can just write down x1 is this and x2 is this. Okay, so this is one example, and the second example is this one here. Looks similar, also again from R2 to R2. So we will do the same thing. This here is a matrix A, and then we try to solve the linear system. So we put here A and Y, 1, 1, 2, 2. y1, y2. So in this case here we subtract the first row twice from the second, and then we see we get zeros here in the second row, and here we have y2 minus 2 times y1. And this is now here the left side is on row-less echelon form, but now we have a row which is 0, so the image is not everything. So this here is now what I denoted by this star at the beginning. So in this case, the image of f are those vectors y1, y2, and r2, which satisfy that this here equals 0. So y2 minus 2 times y1 needs to be 0. And this here is not all vectors satisfy this. So therefore, in this case, f is not surjective. And how about injective? Well, if we take something in the image, so if we have some element in the image, so assuming this here is 0, how many solutions do we get? Well, we now have a free variable. Namely x2 is a free variable because it's not a pivot element here. There are infinitely many solutions for this equation here. So let's make this precise. Maybe just choose one explicit example to show that this is not injective. So for this, we need to choose one element in the image, meaning we just need to find a vector satisfying this. And this is quite easy, because, for example, we can choose a 0 vector. So for example, if y1 and y2 equals 0, then everything here on the right is 0. And what are the solutions? Well, x2 I can choose arbitrary. Say, for example, f of x equals 0, 0 has the solutions well, x2 I can choose arbitrary, so let's say this is some t, And here x1 is just minus t. And then we see that for example, choosing t equals 0, we see that f of 0, 0 equals 0, 0. But also if we choose t equals 1, this is the same. So we can choose f of minus 1, 1. Both of them give 0, 0. But the vector 0, 0 is not the vector minus 1, 1. So f is not injective. Yeah, so choosing y as 0 in the image is maybe always the easiest choice. And then if you look, so let's go to the general case here in the beginning. So if you're at this point here and you see that there's a row which is 0, then you can say, well, I set y equals to 0, then everything here on the right equals 0. And then I can choose some values for the free variables. And then I can say, for the element 0 in the image, I can find this and this solution for the x. So f of this element equals f of the other element, and both of them equal to 0. But these two elements I choose are different, and therefore this map is not injective. And this always works if there are some columns here which do not contain a pivot element. Okay, so let's do example number 3. So now it goes from R3 to R2. Yeah, so first of all, here in this example, it was not surjective and not injective, and in this example here, it was surjective and injective. And the reason here is that these numbers were the same. So actually, if they are the same, we will see that if something is surjective, then it's automatically injective. And if something is not surjective, then it's also automatically not injective. But if these numbers are different, like in this example, then we can also get a mixed case. So it could be surjective and not injective, and the other way around. So let's see how this looks like in this case here. So again, let's first write down what is the matrix in this case. Well, I want to multiply this here with the vector x1, x2, x3. So what do I choose here? So I choose 1, 1, 0, and here in the second row I get 1, 0, and minus 1. So this here is now what we call the matrix A. And again, we want to solve the linear system ax equals y for an arbitrary y. So we write A here, and y in our case is in R2. So this here is 1, 1, 0, 1, 0, minus 1, y1, y2. And here the first step is subtracting this from there. And then you get 1, 1, 0, y1. And here with 0. And now we have a minus 1 here and a minus 1. And here we have y2 minus y1. So then we can, for example, multiply this here with minus 1 to see 1, 1, 0, y1, 0, 1, 1, and here y1 minus y2. And then we subtract this here from there to get this here, minus 1, and here is a y2, 0, 1, 1, y1 minus y2. Okay, so this is now in a reduced echelon form, and we see there's no row which is completely 0. So this means no matter what y1 and y2 are, we can always find a solution. So in this case, the image of f is everything. And this means f is surjective. But how about injective? So if we take something in the image, and in this case we can choose an arbitrary vector, but again we can choose the vector 0, 0. So if y1 and y2 is 0, we see that we have these two pivot elements here, but also there's a column, this one here, which doesn't contain a pivot element. So this corresponds to the variable x3, so x3 is free in this case. So again, we can consider this equation here, f of x equals 0, 0. We find the solutions. Well, x1, x2, x3. Well, x3 can be arbitrary, and if x3 is arbitrary, what is x2? Well, we can put x3 on the other side, so we have minus t, and here it's a minus, so if we bring it on the other side, it's a plus t. So we get these solutions. So in particular, I can again choose t to be 0, but I can also choose t again to be 1, and both of them give the vector 0, 0. Yeah, so you can also check this with the original definition here of the linear map. If I choose the x to be all 0, then of course this gives 0, 0. And if I choose x1 to be 1 and x2 to be minus 1, then this here is 0. And if x3 is also 1, then 1 minus 1 is 0. So this also gives 0. Yeah, so this shows that f is not injective. So in this example, f is surjective, but not injective. And finally, let's do this example. Now it goes from R2 to R3. So again, let's first write down what is the matrix here. So in this case, it's a 3 by 2 matrix. So here it's 1, minus 1, 2, 1, and 0, 1. So this is the matrix A. Again, we consider this here. And now in this case, here 1, minus 1, 2, 1, 0, 1. So y is in R3, so it's y1, y2, and y3. And here we subtract now the first row twice from the second and get this. So here it's 0. Here minus minus gives plus. So 2 plus 1 is 3. And here we have y2 minus 2 times y1. And the last row is still the same. And now maybe the easiest way is maybe changing these two rows and then subtracting from the other 3 times. So let's subtract this 3 times from there, and maybe to save some paper, let's also swap them afterwards. So the first row is still the same. The second row and the end will be this here, so 0, 1, y3. And if I subtract this here 3 times from there, then here I will get a 0. So here we have a 0 row. And here I get, let's write it like this, minus 2 times y1 plus y2 minus 3 times y3. And to bring it on Rhodes echelon form, we could now also add this here 1 times to there. So here we have 0 there. And here y1 plus y3. 0, 1, y3. And here it's still the same. Minus 2 times y1 plus y2 minus 3 times y3. And in this case, we again have a 0 row, meaning the image of f is given by all vectors y1, y2, y3 in R3, which satisfy the conditions which are on the right side for each 0 row. So here we have 1, so this condition here is that this should be 0. So minus 2 times y1 plus y2 minus 3 y3 should be 0. So in particular, this is not everything. So f is not surjective. But if we choose some element in the image for some element in the image, we have a unique solution. Because here, if I have some element in the image, meaning this here is 0, so we can ignore the last row, then we can find a unique solution here for x1 and x2, because there's no free variable. So for an element in the image, we have a unique solution for f of x equals y, and therefore is injective. So in this case, f is not surjective, but f is injective. Okay. Yeah, but I mean, in this example, it goes from f from R2 to R3. But this doesn't mean, so if you look at these examples, you might think that if this number is greater than this, then it's always surjective, and if it's smaller, then it's always injective. But this is, of course, not the case. So maybe let me give you one more example. So, for example, if I would have this here from R3 to R2, by sending, for example, x1, x2, x3 to x1, x2, sorry, there should be something in R2. So let me send this to, let's say, x1, 0. Then, of course, this is a linear map, but this is, of course, not surjective, because the image in this case are just those vectors where there's something in the first row. Okay, but I hope these examples help, and I hope it shows how this general strategy here works.